C-Lion, a cross-platform IDE for C and C++. Download now.
So yes, this is practical tips for safer C++. So I don't know if you've noticed, but safety in C++ has become sort of quite a big topic. Recently, over the last couple of years, everyone seems to be talking about it. A lot of that has been, we've had regulatory pressure coming from the US government, in particular, various branches of the US government saying that everybody should be using memory safe languages and people should stop using C and C++. I mean, who knows whether that's going to continue, but I think the focus on safety is going to remain. And as much as we might like to, we cannot just wave a magic wand and turn C++ into a safe language overnight. Much as we might like to do so, you know, even if we do, it's going to take a very long time to get there. So the purpose of this talk, the idea behind this talk, is that while we can't turn C++ into a safe language, we can make our use of C++ safer by being aware of the source, at least some of the places in which you are likely to trip up, some of the places in which it is easy to fall into unsafety, and by being aware of them and knowing about the alternatives, being able to write safer C++ code. So that is the goal behind this evening's talk. So here in particular is what we're going to be talking about. So I'm going to start off with just a little definition of what do I mean by safety for the purposes of this talk. And then we're going to be talking about numeric safety, bound safety, memory safety. I'm going to talk about a little bit about testing. And then after that, I will be hanging around in Gather. If you want to ask any questions, it's the asynchrony of online makes it a bit difficult to do during the talk. So, but I will be on Gather afterwards if you have any questions. Okay. The other thing to say is that honestly, this talk could have been 2-3 times as long because, well, there is quite a bit of unsafety in C++. So I just picked a few of my, I was going to say favorite, I'm not sure that's the right term, my favorite or least favorite parts to talk about. If I don't talk about your particular favorite bit of unsafety or undefined behavior, then it's not because I don't think it's important. It's just that, you know, there's only limited time. There's only so much time. Okay, so let us begin. Whenever people talk about safety, it's important they give a definition of what they mean by that, because different people have different meanings about safety. I mean, we hear about safety critical software. This is, you know, where lives are on the line and things like that. But I'm not talking about that definition of safety. I mean it in the sort of safe language sense, okay? And in particular, for the purposes of this talk, I'm going to use a definition of safety that comes from another talk by Dave Abrahams. So Dave's a very well-known name in the C++ world. He was one of the co-founders of Boost. He went to work for Apple on Swift for a long time. Now he's working on a language called Hilo, previously called Val. And a couple of years ago, CPPCon 2022, Dave was giving a talk about the Val language as it was then. And he gave this definition of safety. He said, a safe operation cannot cause undefined behavior. Let's blow that up a little bit. A safe operation cannot cause undefined behavior. Now, I really like this definition of safety because undefined behavior is, I forget the exact quote from the standard, but it is behavior for which the standard imposes no requirements, right? Anything can happen, or at least theoretically, anything can happen should undefined behavior occur in the running of our program, okay? And we cannot reason about our programs in the presence of undefined behavior. But it's actually worse than that, because optimizers take advantage of undefined behavior, that undefined behavior can never happen, which means that not only can we not reason about a program that has, run some code that would have UB, if your program has UB anywhere in it, the compiler, in principle, can take advantage of that. And you often see this in lightning talks. People like to write these absolutely crazy examples where you see something that makes no sense happening, and it's almost always because the optimizer has taken advantage of something that can never happen in undefined behavior. So we don't even need our code to reach the point at which UB would occur in order to see strange effects. We say that undefined behavior can travel back in time. It's really scary. If you want to know quite how scary, there's a talk by Fedor Pikus that he gave at CPPCon in 2023, Undefined Behavior, What Every Programmer Should Know and Fear. So it's only a 30-minute talk. It's really good talk, really interesting, pretty scary. But if you haven't seen it, I highly recommend going and watching Fedor's talk. So undefined behavior means that we can't reason about our programs. And if undefined behavior was something that was rare and unusual, well, maybe that wouldn't be so bad. But unfortunately, the C++ language and the standard library make it very easy to accidentally stumble into UB. And as I mentioned, we can't just wave a magic wand and remove undefined behavior from C++ without drastic language and library changes. And since I wrote these slides, actually, now we know quite how drastic those changes need to be, because some of you might know Sean Baxter has he's written his own C++ compiler called Circle, and he has written effectively a dialect of C++ that is safe, that is free of undefined behavior. And he had to make some really big changes to the C++ object model and the way things work, and add effectively a new standard library in order to do this. So maybe one day we will have a safe C++. Personally, it's something I would like to see, but if it ever happens, it's going to take us a very long time to get there. In the meantime, we can take steps to make things safer, and that's really the goal of this talk. Okay. So a couple of disclaimers to get out of the way first. First thing to say is I'm not a safety or security expert. I'm just a guy. This talk is based on my personal experience of having used C++ for many years, from having taught beginners, from having taught people who are very experienced in other languages, and seeing where they trip up, where they struggle when they switch to C++. I already mentioned this talk is far from comprehensive. I could have made it at least twice as long, but hopefully you will find it interesting. My second disclaimer, again, some of you might know, I'm the author of a library called Flux, which is primarily its purposes kind of iteration algorithms, sequence adapters, things like that, a bit of an alternative to C++ 20 ranges. But one of the things Flux tries to do is to make coding in C++ less prone to accidental UB. So this talk is not about Flux. I have given talks on the library in the past, if you want to go and find them. This isn't a Flux talk, but it so happens that it's just a code base I know well, and it's I've got lots of examples, several examples that come from that library. So I am going to end up mentioning it. So I'll just get the advertising out of the way right at the beginning. So if you are interested in learning more about Flux, you can find the URL is there. It's on my GitHub. Otherwise, please do come and talk to me about it, because I'm always happy to talk about it. Right. With all of that out of the way, let's plow on to our first topic for the evening, which is numeric safety. All right. Consider the following function. Now, if this were an in-person conference, I would get people to raise their hands here. But what I want to know is, given our definition of safety, is this a safe function in standard C++? Have a think about that for a moment. And the answer is, for those who didn't know, no. This is not a safe function by our definition of safety. Our definition of safety, we cannot have undefined behavior. This function can exhibit UB. So for example, if we call add and we take int max and we add 1 to it, this is going to cause signed integer overflow, and signed integer overflow is undefined behavior according to the standard. So that's, right off the bat, that's pretty bad, because this is kind of the simplest function you can imagine writing in C++ or in any language really, and this is an unsafe function. So that's not great. So why are things this way? Well, leaving sign overflow undefined allows the compiler to assume that it will never happen, and it kind of allows our integers to be a better model of a mathematical integer, strangely enough. It means that kind of obvious optimizations can be applied. So for example, just mathematically, just from maths, we know that if we have 3 and we add x and then we subtract 3, we're going to end up with x. That's just kind of makes sense. But the compiler can only make this optimization if we allow it some leeway. Similarly, from maths, we would assume that x is always less than x plus 10, or x is always going to be less than x plus a positive constant, right? It's just the way math works. But again, doesn't necessarily work that way for ints unless we allow the optimizer some leeway. And the same for the associativity of addition. So this is one of the reasons why historically C and C++ have allowed integer overflow to be undefined, because it allows ints to work kind of more the way that we think mathematical integers should work. But we have other kinds of integers other than signed ones. We have unsigned ones. So another question to ask is this a safe function? So all I've done is change int for unsigned int. So is this a safe function? Well, the answer to this one is yes, it is, for our definition of safety. Because unlike with signed integers, unsigned overflow is well defined in C++. If we take uint max and we add 1 to it, we're guaranteed to wrap around and get 0. And this means that most of the operations we do on unsigned integers are not UB. But that doesn't mean that they're not problematic. I would say that probably, I don't know, 90% of the time, maybe more, 95% of the time that you get that you wrap around an unsigned int is probably a bug, right? Because who hasn't accidentally tried to allocate an array of 18 gajillion elements, or try to access element -1 of an array and it's wrapped, size t is wrapped around. I've done this. It feels like I've done it that many times. I don't know if I have, but certainly feels like it. So I don't know if you are, if everybody, is aware of this, but apparently, so I've heard, there is a new programming language around called Rust that some people seem to be quite keen on, that promises to do away with all this unsafety. And as well as Rust, there's another language. It doesn't quite get as much hype, but it is a safe language and it is very popular in its sphere, which is Swift. Which again, both of these exist in the same domain as C++. So what do Rust and Swift do with this problem of integer overflow? Well, in Rust, integer overflow, both signed and unsigned, it causes what's called a panic in debug mode. That effectively means it crashes your program. If you compile in release mode, then we get the wrapping behavior. That is the same as we get with unsigned ints in C++. The Rust standard library has functions that you can do explicit wrapping, even in debug mode. You can have explicit checked operations, even in release mode, and it also has unsafe, unchecked operations. This is pretty nice. Swift is pretty similar. So in Swift, integer overflow causes a runtime error. That is, again, it crashes your program in the debug mode and in the default release mode. But it also has this -o unchecked, which relaxes some of the checks. And in that case, it will wrap around rather than trap it. Swift is kind of unusual. I don't know of any other languages that do this, but Swift actually has some built-in operators for ints that do explicit wrapping. So it has ampersand plus, ampersand minus, etc. that allow you to do explicit wrapping operations. It also has some standard library functions, add with overflow and friends, for doing explicit overflow checks. As far as I know, there's no way to get to do unchecked integer operations in Swift. I'm not a Swift expert though, so perhaps there are, but from a sort of, as far as I know, it doesn't exist. So that's what Rust and Swift do. People seem to like them. They're considered safe languages. Can we do in C++ what Rust and Swift do? And the answer is we can get very, very close to it. So in GCC and Clang, there is a compiler option -f wrapv. -f wrapv. And what this does is it gives signed integers wrapping semantics. So effectively, signed integers behave in the same way that unsigned ints do. So you're guaranteed that if you overflow the end of a signed int, you're going to wrap around to negative. So this functions like release mode does in Rust. This means that there is no unsafe behavior on overflow. The compiler is not going to optimize assuming that overflow never happens. But it does mean that a few optimizations can no longer be applied. So for example, this inequality. So if you think about it, if x was int max and we add 10 to it, we're going to wrap all the way around to a very negative number, which is going to be less than the int max, the positive int max we started. Okay, so things like this can no longer simply be optimized to true. But most of the time, that is probably worth a worthwhile trade. So that's fwrapv. There's another similar compiler flag, which is ftrapv. And this makes signed overflow trap. That is, perform an illegal instruction, the operating system is going to kill your program. It's going to crash your program. So Clang has ftrapv. GCC does as well, but in my experience is that it doesn't actually work very well in GCC. That actually doesn't matter because with both of these compilers, UB Sanitizer is a more comprehensive alternative. So UB Sanitizer can do everything that this ftrapv option can do. So you can compile it like this. This is GCC, but it's the same command line in Clang. So you say -f sanitize equals signed integer overflow, and that's going to enable these signed overflow checks, and it's going to crash your program. And you can also say -f sanitize trap. This means that you don't have to link to the UBSAN runtime, just makes your binary smaller. So the really nice thing about this is that there is another option, fsanitize equals unsigned integer overflow, which does the equivalent checks for unsigned integers, right? So unsigned integers, as we've seen, it's not undefined behavior, it's well-defined, but it's usually a bug. And with this UBSAN option, you can actually have the compiler, or have the compiler insert checks to make sure that your unsigned ints don't overflow either. So this is equivalent to the debug mode in Rust or the default mode in Swift. And in fact, if with Clang, it is precisely equivalent. You can look at the generated code in Compiler Explorer, and it's using, I assume, exactly the same LLVM instructions so you get precisely the same generated code, which is rather nice. And unlike most sanitizer options, so I'm going to mention sanitizers a bit later on, but unlike most sanitizer options, you definitely shouldn't run in your production code. But these, as far as I'm aware, this particular UBSAN option is fine to use in production build if you want to do it. So not other UBSAN options, but these ones are fine as far as I know. So like wrapping arithmetic, checked arithmetic does inhibit certain optimizations. So there's this blog post from Daniel Lemire where he measures this. He said, how expensive is integer overflow trapping in C? This gives some rather dramatic numbers. The reason for this is because checked arithmetic in general will prevent auto-vectorization. The reason for that is that SIMD hardware generally it just has no way of signaling that overflow has happened, right? It just wraps around. So if you enable this the trapping, either with -f trap-b or with UBSAN, you're probably not going to get auto-vectorization unless the compiler can be very clever. So this means that in release builds or in tight inner loops, we probably prefer wrapping or unsafe behavior. Okay. If you are not using GCC or Clang, or you don't want to or cannot change your build flags, or you want to leave the option of unchecked operations on the table, an alternative to changing your compiler flags is to use libraries that provide safe integer functions. So there are several of these available. So just 3 examples. SafeInt is one that came out of Microsoft, I think probably 15 years ago, maybe longer. It's been around for a very long time. It was used originally in Microsoft Office. I think it's used in many projects now. Boost safe numerics is, as you'd imagine, from a Boost library, very comprehensive, kind of very template heavy alternative. Does all sorts of things, can have bounded integers and all sorts of things. And Flux we have just because I thought I'd mention it. We have various checked arithmetic operations in there as well that we use internally, but are also available for users, friend users, if you want to use those. Actually, the I think C23 is going to come with a few checked integer operations as well. So it's very likely that those are going to be available in the C++ compiler. So check those out as well. Some libraries, so particularly Boost Safe Numerics, they actually provide replacement integer types. So rather than having to call a function with, safe add a comma b, you can just do a plus b, where a and b are like these safe int types, right? So if that's appropriate, then that's something you can do as well, because it means that you can just use the regular operations. They just call safe functions. And unlike setting compiler flags, if you use one of these libraries, you retain the ability to use unsafe operations when absolutely necessary. If you really have to. Okay. So that was a lot about integers, but at least floating point numbers are fine, right? Aren't they? Well, here's this question again. Is this a safe function? So I'm taking a vector of floats by reference, and I'm calling standard sort, just passing vec.begin and vec.end. Is this a safe function? The answer is no, it is not. And it's a bit of a different reason from what we've seen so far. So the reason this is not is because of the potential for nans. So nan is not a number. So this is part of the IEEE 754 floating point spec, and nans are not a number. They occur when you do something that mathematically doesn't make sense. 0 divided by 0 or infinity divided by infinity, things like that. And under the IEEE 754 rules, nans are unordered. So all of the operations A equals B, A less than B, and B less than A, all of these return false if either A or B is a nan, right? And this means that using the default less than operator on nans is not a strict weak order. And standard sort, amongst several other standard library algorithms, requires a strict weak order requires its comparator to model a strict weak order, right? So this means that it is undefined behavior to call standard sort on an array containing nans when using the default comparator. And this can actually be a problem in real world code. So here's a bug report from GCC. It is a little bit old now, but as far as I know, this hasn't changed. This caused memory corruption because there was a vector of floats or a vector of doubles in that case, and the unorderedness meant the sort algorithm was reading out of bounds, and that was causing memory corruption. So this can actually, it's a real problem. Okay. So what can we do about it? Well, first thing we can do is make sure that we don't have any nans in our data. If we have actual floating point numbers, then we're not going to have a problem. But we can't always be sure of that. The good news is that the IEEE 754 standard does actually define a total order for all floating points values, including nans. Okay, it's just not the default operator less. And in C++, we have access to this using the function standard strong order. So this was something that came in as part of the spaceship stuff in C++20, this three-way comparison operator. And if we use standard strong order, we can sort our floats according to the IEEE total order. It also, sorts things like -0 compared to +0 as well, which is nice. So we can write a version of sort floats that we can pass it a lambda, which calls this standard strong order function. And if we do that, then we are not going to get undefined behavior, even if our vector contains nans. So this is, again, I just included this because I think many people probably haven't seen this. I know it's one of those, it's like everybody's first Stack Overflow question when they start using Rust is, why can't I sort of a vector of floats in Rust? And that's because of this thing about the total order. So in C++, we've got a way around it as well. We can use this standard strong order function just like this. And the other thing to say is I'm using the float here, but I mean floating point types in general. So float, double, long double. Yes. Okay. Whew. That is it for numeric safety. You'll be pleased to know. So let's summarize what we've learned in this chapter. First of all, if you didn't already know, signed overflow is undefined behavior. Compilers can and they do optimize around this. Unsigned overflow is not UB, but it's usually not what we want. GCC and Clang have compiler flags which can change the default behavior. And in my opinion, trapping in debug mode, wrapping in release mode is probably reasonable for most use cases. As an alternative, you can use a library which offers safe integer operations. There are several available. So take a look at those. And also be aware that floating point data containing nans can cause UB with certain standard library algorithms and just other code that isn't expecting nans. In particular, for the standard library algorithms, you can use a custom comparator which wraps this standard strong order function, which avoids that. So something to be aware of. Okay. Much shorter chapter, this one. Bound safety. Okay. I'm sure everybody already knows this, but in C++, array access is unchecked. So we have an array of 3 elements. We ask for element number 100,000, and the compiler is just going to transform this into an expression where it takes the address of the start of the array, it offsets that pointer by 100,000 places, it tries to dereference that pointer, and that's undefined behavior, right? Default array access is unchecked. Hopefully, modern compilers, you get a warning about this, but you know, it's not guaranteed. Very sadly, and I think this was a bad mistake when they were specifying C++ all those decades ago, is that this is also the case for the default square brackets operator on standard array, standard vector, standard span, etc., etc. Right? The default square brackets operator is unchecked, is unsafe. And this really is a major problem. This is a major problem. Out-of-bounds reads and writes are among the most common causes of software vulnerabilities. So this is from an organization called MITRE. They compile lists of, they've done so for many years, lists of the most common causes of CVEs. And in 2023, which is the most recent that was available when I made these slides, out-of-bounds reads and writes were causes, the second and third biggest causes of software vulnerabilities. Right, so this is a real problem. So what can we do about it? Well, the good news is that most standard library containers do allow us to offer the option of bounds checking via the at function, and this is going to throw an exception if the requested index is out of bounds. So just use it. Problem solved, right? Well, maybe not. For a start, standard span doesn't provide a .at function. I proposed it back before C++20. The proposal wasn't accepted then. More recently, someone else has proposed it for C++26, and it's now been accepted. So that's really good. But we are probably not using C++26 compilers, at least at the time at which I'm giving this talk. This also doesn't help for raw arrays, for initialized lists, for random access views, etc., etc. And there are other people who just can't use exceptions for various reasons or don't want to use exceptions. So .at is great when you can use it, but what if you can't? Well, there are a few options. So one option is that we can write our own generic bounds check at function, which works for all random access size ranges. So it looks like this. I'm not expecting anybody to copy and paste this now, but the slides will be available after. If you want to take this and use it, you're very welcome to. This particular function throws an exception if the index is out of range. But you could modify that to call terminate or to do whatever you like. You could also modify it to return an optional or expected or something like that, depending on what you wanted it to do. Another option, and of course, again, I'm bound to mention this, is to use a library which is designed around giving you safe access to your sequences, such as Flux. So in Flux, we have a pair of functions. We have read at, and what read at is going to do is it is bounds checked. So if you ask for element 100,000 in a 3-element array, this is it's either going to terminate, call standard terminate, or it's going to throw an exception depending on how you configure the library. But either way, it's going to be bounds checked. And in Flux, we also have this read at unchecked function. So this is deliberately long, horrible, ugly name to make it very clear in your source code that this is something you have to pay particular attention to. This is something that is, potentially dangerous. So we deliberately give it a long name, give it a name that tells you exactly what's going on. So those are two alternatives. If you're going to be doing indexing, use bounds checking. What's even better than that? Well, even better than that is to not do manual indexing at all. Eliminate the need for bounds checks by using looping constructs that don't expose indices or iterators. Okay, the canonical example being, of course, the range for loop. But also, your standard library comes with over 100 algorithms that can perform an enormous number of things that you will need to do in your programs without the risk of you getting off by one errors, etc., making mistakes, causing out of bounds accesses. These are well-tested, reusable algorithms that reduce the probability of you making mistakes. No raw loops, as a wise man once said. And by the way, if you haven't seen the C++ seasoning talk, this is Sean Parent's famous talk, then please do go and watch it now. Just drop what you're doing and go and watch it. So people often worry about the cost of bounds checks because, we're C++ programmers, we care about performance, that's why we're using the language. Compilers are surprisingly good at eliding bounds checks, that is, seeing where they are necessary, but there can be runtime overhead in some cases. So my advice, and I've just mentioned it already, but if you do need to, well, first of all, measure. And if you measure and you see, okay, well, if I turn on bounds checking, this function is like 1% slower, but I can't afford 1% in this case. Well, first of all, make sure you do the measuring, but then try to make it very obvious in your code that unchecked access, something unsafe is going on. Okay. Give the function a big ugly name, or write a big comment. It's like, careful, look at this. The other thing to say is there are some neat techniques that you can do to try and, well, basically encourage the compiler to skip bounds checking. So giving the compiler certain bit more information in certain scenarios. So there's one nice blog post here. This blog post is based on Rust, but it actually it applies to C++ as well. So again, you can have a read of that if you're interested. So to summarize, array access in C++ is unchecked, as I'm sure everybody knows, including for vectors, arrays, etc. by default. This is one of the most common safety problems, one of the most common causes of software vulnerabilities. It is serious. So my advice: use .at when you can. If you can't, then implement bounds checking somehow, right? If you need to do manual indexing. So use a generic bounds checking function or a library or some other means of bounds checking. Or even better than that is to avoid the need for manual indexing at all by using standard library algorithms, which don't risk bounds violations. And finally, if you really do need to use unchecked indexing, at least try to make the fact that it's unchecked really obvious in your code, so the next person who goes to make changes is aware that they have to be really, really careful in this particular place. Okay, time is really moving on, so I've got to be quick and move rapidly on to the next chapter, memory safety, which is, I'm sure this is going to be a quick chapter, right? There's not too much to say here. Right, so let's state the obvious. C++ is not a memory safe language, right? Again, it's something everybody attending this conference already knows. So here's just one example of a way in which it might be a way in which it is unsafe. So we're creating a pointer to an integer. We're initializing that to null pointer. Then in an inner scope, we're creating an integer I. We're setting pointer to the address of I, and then at the curly brace, the scope in which I is declared ends. The object I is destroyed, and PTR is left holding the address of a deleted object. So when we try to dereference the pointer in the call to print, this is attempting to access a memory location that doesn't have an object. There is no object there. So this is undefined behavior. This is classic dangling pointer example. Now, if this only happened with raw pointers, perhaps it wouldn't be so bad. But it's not just raw pointers. This kind of thing can happen very easily with many different reference-like types, reference-like things in C++. It can easily become invalidated. We can easily get use after free, etc. So not just language pointers, we have language references, we have iterators, we have standard string view is a reference type, standard span is a reference type, standard reference wrapper, well, that one's pretty obvious. Lambdas, which capture reference-like types, can themselves become invalidated. Right. So if you have a lambda that captures a string view, or a lambda that captures the this pointer in a member function, right? We have to be careful about lifetimes in those cases. And there are other examples as well, but I think this is enough of a list beginning on. So how do other languages deal with memory safety? Well, a lot of languages, they do it with a garbage collector. That is not C++. And recently, by which I mean in the last decade or so, we've had other languages which are also non-GC'd, generate native code, but offer memory safety. And again, Rust and Swift. So how do they do it? Oh, sorry, I've skipped my slides. I apologize. I just wanted to show you another example, and we'll come back to Rust and Swift in a second. But just on the subject of invalidation in C++, it can be really tricky to spot when invalidation is happening if you're not really thinking about things very closely. So here's an example involving iterators. So if you are new to C++, if this is maybe you're a Java expert who uses C++ occasionally or whatever, it's not necessarily obvious that something weird is going on here, and yet there is a bug in this code. And what's even worse is that this code might work perfectly well for 20 years, right? Because, well, what's going on? Well, we're creating an iterator to the start of some vector, vec, okay? And an iterator is effectively like a pointer to the start of vec's internal storage. And then we're calling pushback. And then after that, we're using iter again. Now, if the vector happens to be full, and to be at capacity at the point at which we call pushback, then this is going to cause a reallocation. The vector is internally going to allocate a new array. It's going to move everything from the old array into the new array. It's going to delete the old array. And then iter is going to be effectively like a dangling pointer. But like I say, this is only going to happen if the vector happens to be at capacity at the point at which we call pushback. Most of the time, it probably won't be. Most of the time, you're going to get away with this. This is like a time bomb sitting in your code base, right? And it's really hard to spot unless you know what to look for, unless you know that pushback is documented to invalidate iterators. Okay, so back on the track. How do other languages deal with this? How do Rust and Swift deal with this? On Rust, Swift, and Hilo, which I mentioned briefly earlier, they achieve their safety, all of them in the same way, they do it by enforcing something that is called the law of exclusivity. This is some terminology that came out of the Swift language, the law of exclusivity. And what the law of exclusivity says is that modification requires exclusive access to an object. Modifying an object requires exclusive access to that object. In other words, we cannot safely modify an object whilst anybody else has a reference to it. So this is the safety principle underlying Rust and Swift and Hilo. In the Rust world, this is often explained as shared or XOR mutable, right? You might have heard that if you've seen anything about Rust in the past. This means that at any point in our program, we can have at most one mutable reference to an object in use, or any number of const references, but not both at the same time. Okay. So here's the thing, and this is a very powerful statement once you realize it, is that if we can obey the law of exclusivity in our C++ code, we could have memory safety in C++ as well. If we can write C++ that adheres to the law of exclusivity, our C++ is memory safe. And that's quite a sort of powerful thing to realize and to think about. And we can, now that we know about the law of exclusivity, and if we keep it in our minds, and if we think about it, well, we can look at the example that we saw before with iterators. We can look at it through the lens of the law of exclusivity and kind of work out what's happening. Because as long as we know that C++ iterators, as with iterators in most languages, are reference-like types, well, we begin to see what the problem is with this little code example. So our iter, when we create it, iterators are reference-like. So now, while iter is alive or while iter is in use, we are holding a reference to vec. And then when we call pushback, we are modifying vec, but we're modifying vec whilst somebody else or whilst other parts of our code is holding a reference to it. So this is a violation of the law of exclusivity because we're modifying it, but we don't have exclusive access. And sure enough, when we use iter later on, we're going to wind up potentially with undefined behavior. Not guaranteed, but potentially. Okay, now the law of exclusivity is sufficient to prevent memory safety errors. It's not necessary. That is, if we violate the law of exclusivity, it doesn't automatically mean that our code is unsafe, but it does mean that we should be very careful about what we're doing, and we should look very carefully to make sure our code is correct. So, if we can obey the law of exclusivity, we get safe C++. That sounds great, but in my opinion, at least, without language and compiler support, strictly adhering to the law of exclusivity, kind of just by trying really hard in large-scale, real-world, perhaps 20-year-old C++ code bases, is going to be phenomenally difficult. We basically have to act as like human borrow checkers, and people have enough problems with the programmatic borrow checker in Rust, let alone trying to do it in your head. So this is going to be phenomenally difficult. However, if we can have the law of exclusivity in our heads while we write our code, while designing our APIs, we can still avoid some common errors. So in particular, if we write our APIs in such a way that the formation of references, particularly long-lived references, is explicit, then we can make data and lifetime dependencies more obvious, and this can help to highlight violations of the law of exclusivity, that is, potential problems, potential data, and potential lifetime and memory safety issues in our source code. Okay, so I'm going to give a brief example. Again, it's taken from the Flux library just because it's a code base that I know well. So the way we pass parameters to adapters in Flux. So in Flux, you can build up pipelines of sequence adapters, a bit like chaining views in C++20. But in Flux, things work slightly differently because our sequence adapters are sinks. That is, they take ownership of the sequence you pass into them. So if you pass a vector into a filter adapter, the filter adapter will take ownership of that vector. Okay, so adapters, these adapter functions in Flux, they take their arguments by value, effectively. Of course, we don't always want to copy a vector into the adapter. That could get quite expensive. So Flux also lets you operate on a reference to a sequence, such as a vector. But in order to do so, you need to explicitly create a reference wrapper object. And it's the reference wrapper object that gets passed by value. So we have a function fluxref. And what this does, it creates a read-only reference object referring to some other sequence. Okay, so this is very much like a standard reference wrapper of const s for some sequence s. And also in Flux, we have this muteref function. And this creates a mutable reference object referring to some other sequence. Okay, so this one is like just reference wrapper of s. Now, you'll notice if you know about these, that this is the opposite way around to the way the standard library does it. And that's because I want ref to be like the default thing, the thing with the nice short name. And I want muteref because ideally, we only ever want there to be one mutable reference at a time. So I want it to be more obvious when you're creating a mutable reference. And again, if you create a mutable reference, that object is move only. All right, it's not foolproof, but it's just a little speed hump that kind of prevents you from really easily creating multiple mutable references. Okay, so it doesn't prevent it. It just makes it a bit more inconvenient to do it. All right, so here is our function that we're going to be looking at. This is the zip adapter in Flux. It works a lot like viewZip in C++23. We take a pack of sequences and we return some sequence object that iterates over all of the passed in sequences in lockstep. And we're going to create a few of these zip objects. So in the first case, we use this operator auto to create an explicit copy of some vector vec. And in this case, we can see we are making an explicit copy. So we know that Z1 has no data or lifetime dependency, right? We are copying the vector, we're taking ownership of it. So there is no data or lifetime dependency. And similarly with Z2, this time we're moving the vector into the adapter object, but this time, again, there is no data or lifetime dependency. With Z3, on the other hand, what's happening now is we are explicitly taking a reference to vec. So you can look at this source code, and just by looking at it, you can see, okay, Z3 has a data and lifetime dependency on vec. So I have to ensure that vec lives longer than Z3. And, well, I have to be very, very careful if I modify vec while Z3 is in use. Right? So it is right there, obviously, in our source code. We can take references to a couple of other vectors, and this is fine. So Z4 now has dependencies on 2 vectors. We have to be careful about lifetimes. But again, it's right there in our source code, what the dependencies of Z4 are. We can take 2 const references to the same object. That's absolutely fine. Okay, this is not a violation of the law of exclusivity. We can have 2 const references to the same object. That's no problem. However, Z6, here we're taking a const ref to vec and a mutable ref to vec, and this is, at the very least, suspicious. we're taking a const reference and a mutual reference to the same object. This is a potential violation of the law of exclusivity. Are we 100% sure that this is correct? This is something we're going to have to look at very carefully. Okay, so this is, this is not foolproof. This is kind of trying to help us to obey this law of exclusivity. It's not foolproof. There are any number of ways around it, but it's a way of trying to reduce the potential for making mistakes. So I am almost out of time, but to summarize this chapter, C++ is obviously a memory unsafe language. Newer languages, Rust and Swift, they operate on the basis of the law of exclusivity that is used to ensure memory safety. Modification requires exclusive access. And in principle, if we were to adhere to the law of exclusivity in C++, we would get memory safety as well. However, this is probably impossible in practical code bases, real-world code bases without language support, which I hope we get one day, but it will take a long time to get there. Having said that, careful API design in order to make as much as we can lifetime and data dependencies more obvious in our code reduces the possibility of making mistakes. But it's just a helper. It's no silver bullet. So be careful out there. Okay. I do have one chapter left. It's quite a short chapter, so I'll just race through it in a couple of minutes. I was going to say it's I don't want to delay whatever you're going to do, but actually this is the last session, isn't it? So it really doesn't matter. I can just carry on talking. Let's keep the conference going. We don't want to end, do we? Let's just keep it going. All right. So testing. I see a couple of thumbs up, so thank you. Yes, just a little warning. Actually, this next slide is a little bit scary. Just for those who are of a nervous disposition. Here we are. So this is I took this from the JetBrains Developer Ecosystem Survey, the 2023 edition, when I was preparing these slides. This stunned me, this little fact, because if this is to be believed, some 29% of C++ programmers say they don't write unit tests for C++. This seems to me like astonishing. And it's gone up. Like, it was only 26%. Now it's 29%. This is very worrying, in my opinion. Don't be one of the 29%. Testing is really, it's important in all software domains, right? It doesn't matter what language you're using. It doesn't matter, almost doesn't matter like what domain of software you're working in. You want to make sure that your software functions correctly. And the way to, the best way to do that is by writing tests to make sure that it operates correctly. But this is particularly true in a language like C++ that offers so few guarantees in the language itself. So there are many conference talks on how to write good unit tests. They're very much worth watching. I'm not going to repeat the advice here. They're all packed with useful information. If you want just one to get started, and as I say, this is like a staple of conference lineups, conference schedules, how to write good unit tests. But here's one in particular. This is Programming with Guts, Good Unit Tests by Kevin Henney. I think he's given this talk a few times. This particular one's from Meet in C++. But yes, by Kevin Henney, our keynote speaker from Wednesday. So if you're looking for somewhere to get started, this is one. But really, there are lots of these talks. So please do go and watch them. But there was just one thing that I briefly wanted to bring your attention to, if you haven't seen it, which is one useful technique that perhaps people haven't seen before, which is context testing. So here's a quote from the standard. It says that an expression is a core constant expression unless blah, 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 an operation would have undefined behavior. What is this saying? It's saying the compiler is required to diagnose undefined behavior that occurs during compile time evaluation. Okay? Compiler is required to diagnose language UB that occurs during compile time evaluation. And what does this mean? It means that we can write a context test, we can evaluate it using static assert, and we gain a free compile time UB check courtesy of our compiler. We have the compiler, which is, after all, the ultimate arbiter of what is undefined behavior. We have the compiler telling us this is UB, right? Brilliant. So here's just a little example of how you can do that. We're going to go back to our add function from right at the beginning. And then we're going to write a context test add function. Okay, so we're just going to test to make sure that add 3 plus 4 is 7. So if it is not, you can wrap this in a macro, but this is what it might look like. So we're going to throw, you can't have an exception, can't leave a function in context, so this is going to result in a failure. And it's actually, if you using a throw statement, means that the compiler will end up telling you exactly which line has failed. So this is quite nice if you use a throw here, even if you attempt to throw at compile time, it's going to tell you which line failed. So, okay, we test and we make sure that add 3 plus 4 is equal to 7. We had a bunch of other tests. And then we're going to test to make sure that int max plus 1 is equal to int min, right? So we test, even though we know what's going to happen, but, theoretically. All right. So that's our test add function. And then we're going to static assert that this test add function returns true. And the static assert ensures that the compiler is going to run this function at compile time. And what happens when we do this? Well, this is the exact output that I got from Compiler Explorer in GCC. It tells us exactly what the problem is. It tells us we have an overflow in the constant expression. It tells us exactly the line where the problem was. It is saying this is UB, right? It is telling us that the add function, it was the very first question I asked in this, is this a safe function? No, it's not, because it has UB, and this is the compiler confirming it for us. So here is my suggestion, is to make functions context whenever you can, whenever it is feasible to do so, even if you, in the running of your program, you don't need it to be context. If you can, write context tests, you can run these tests at compile time and check, at least for a subset of possible inputs, whether your functions have UB or not. Okay, if you have a concern about compile times, I would understand that. You can do this, you can place if-defs around them. You can have certain build modes where you're going to run your context tests, at build time, and maybe you do that somewhere else where run it overnight or whatever. These things are possible. Context tests are, in my opinion, probably our best defense against undefined behavior. Pretty much the whole of Flux is tested this way. Actually, since I wrote this slide, I learned that not only that, pretty much most of the libc++, all of the ranges and the algorithm stuff is tested precisely using this exact same pattern. So the standard library itself uses this pattern to do context testing. So just very briefly to finish up, if you can't do this context testing, the next best defense against UB is probably using sanitizers. So GCC, Clang, and MSVC, they all have various sanitizers available. So there's the UB sanitizer, which detects some forms of undefined behavior at runtime. There's address sanitizer, which detects memory errors. There's memory sanitizer in Clang, which detects the use of uninitialized memory. There's thread sanitizer, which detects data races. You can run your code with all of these sanitizers, or as many as you can. run your tests with these, both in debug and release configurations, because they will help you detect programs. And if you can, compile regularly with more than one major compiler, because they all have different warnings, different things that they will pick up on. So your code quality will go up if you compile with multiple compilers, for sure. And obviously enable all the warnings you can without false positives, because your compiler is trying. And the last thing to stress is that these approaches, whether it's the context for testing or the sanitizers, these only find problems in code that they execute. So thorough tests are essential. Don't be one of the 29%. Okay, that was a brief little chapter at the end. So yes, apparently lots of people don't write tests, but use context for testing. Build your tests with sanitizers, and use multiple compilers if you can. All right. I have run over time. I am keeping the conference going, but it is probably time to finish up. So the absence of undefined behavior, to summarize this whole talk, the absence of undefined behavior is a prerequisite for safe code, right? And there are many kinds of UB that can occur in C++. We've touched on a few of them here, but this is just the tip of the iceberg. If you are programming in C++, you need to be aware of at least the most common places in which you can trip up, and libraries and coding techniques and ways to avoid them. Please write tests. Please write tests. Whether you are trying to detect UB at compile time or runtime, there are ways of doing it. It's dangerous out there, but good luck, everybody. That is it. Thank you very much for listening, everybody. I will be in Gather very, very shortly. But yes, thank you for hanging around. I hope you've all had a great conference. I have. And see you all in Gather in a few minutes. Thank you, everyone.